Did you know that mathematics is broken? It has always been broken, but we didn't know until 1931, when an Austrian mathematician named Kurt Gödel showed that it is. What do I mean by broken? In 1920, David Hilbert, a German mathematician, proposed a program to formulate a solid foundation for mathematics. In the latter 19th century, mathematicians like Bertrand Russell and Alfred North Whitehead were digging deep into mathematics to try and get to the bottom of it. That is, to come up with a set of, let's say, rules and definitions that would be the foundation of all of mathematics. But some problems had come up. In 1920, Hilbert proposed a project that would finally resolve all of these problems and put mathematics on a solid foundation. Unfortunately, in 1931, Kurt Gödel showed that it can't be done. He proved that there are true mathematical statements that can't be proved. I'm not going to get into any more detail about how mathematics is broken, except to say that where and how it's broken is very far away from most of the interesting mathematics that people actually do, and doesn't invalidate any of it. I'm also not going to get into Gödel's proof and exactly what it says about mathematics. What I'm going to do is look at a clever technique that Gödel used in his proof. Many numbers can be said to be interesting because of some inherent property, such as being a perfect number, or being a Mersenne prime, or being the greatest or smallest number with a certain property. Instead of focusing on some number's inherent properties, I'm going to construct a number that, as far as I know, has no particular properties that make it different from any other number. What makes the number interesting to me is the process by which it is constructed. I'm going to use the process that Gödel used in his proof to construct a number that is my favorite number, over 1 million, not because of its properties, but because of how I arrive at it. The technique, which we now call Gödel Encoding, is a way of uniquely encoding any mathematical statement in a single number. The technique is based on prime factorization. Every whole number can be expressed in a unique way as a product of prime numbers. For example, 90 equals 2 times 3 squared times 5. 91 equals 7 times 13. Using Gödel encoding, we can take a sequence of numbers and encode it with a single number by making each of the numbers in the sequence the exponent of a prime number, and then multiply everything all together. Here are the first few prime numbers, which we will use as the basis of our encoding. Let's say we want to encode the sequence 1, 2, 1. The first number in the sequence is 1, so we use it as a power on the first prime number. The first prime number is 2, so we have 2 to the power 1. The second prime number is 3, so we have 3 to the power 2. And the third prime number is 5, giving us 5 to the power 1. We multiply all that together. 2 to the power 1 times 3 to the power 2 times 5 to the power 1 equals 90. So the number 90 encodes the sequence 1, 2, 1. It's possible to go the other way, that is, to decode any number into the sequence it represents. Starting with 90, we find how many factors of 2 it has, which is 1, giving us the first number in the sequence. Then how many factors of 3, which is 2, giving us the second number in the sequence. Then how many factors of 5, giving us 1. In the case of 91, we look for the number of factors of 2, which is 0. So 0 is the first number in the sequence. Then the number of factors of 3, again 0. Factors of 5, 0. Factors of 7, 1. Factors of 11, 0. And 13, 1, giving us the sequence 0, 0, 0, 1, 0, 1. Any set of symbols can be represented with numbers. Just line them up and assign unique numbers to them. For example, if we want to encode words, we can represent letters with numbers, the letter A with 1, the letter B with 2, and so on. If we want to represent the word and, A is represented by 1, N by 14, and D by 4. Our list of numbers is 1, 14, 4, which is encoded as 2 to the power 1 times 3 to the power 14 times 5 to the power 4, which equals 5,978,700,000 711,250. Gödel's proof depends on being able to represent any mathematical statement as a single number. So he listed the symbols that were necessary for the mathematics he was using in his proof and assigned them numbers. The mathematical system in which his proof is stated is basic logic. P implies Q, Q and not R, etc. It's not necessary that you know about basic logic to understand the number I'm going to construct, except that the variables in the system, P, Q, R, etc., stand for mathematical statements that are either true or false. For instance, P could be 1 plus 1 equals 2, and Q could be 1 plus 1 equals 3. In this case, P is true and Q is false. Both are mathematical statements that we can represent as numbers. There are any number of ways to encode a system like mathematical logic in Gödel's encoding. I've come up with what I think is the simplest statement in mathematical logic and encoded it using the system outlined in Gödel's original paper. The statement I will encode is this: P or not P, which simply means that every statement is either true or false. That is, if P, whatever it is true, then not P is false. On the other hand, if P is false, then not P is true. Here's an excerpt from Gödel's paper describing the specifics of the encoding system he used in his proof. In his system, the OR symbol is numbered 7, and the NOT symbol is numbered 5. Variables, which in basic logic stand for mathematical statements, are numbered with prime numbers starting with 17. So P, our variable, is encoded as 17. The sequence of numbers that are given to the symbols in my statement, P or not P, is therefore 17 for the variable representing any statement, 7 for the symbol meaning OR, 5 for the symbol meaning NOT, and 17 for the variable. The Gödel encoding of my sequence is 2 to the 17th power times 3 to the 7th power times 5 to the 5th power times 7 to the 17th power, or 131,072 times 2,187 times 3,125 times 232,630,513,987,207, which equals 208 septillion, 389 sexillion, 297 quintillion, 803 quadrillion, 272 trillion, 892 billion, 6,400,000.